Hello, I'm Dr. Tom Walla, and today I'm going to talk about analysis of variance. And I think if you want to look right here, the analysis of variance is based on a really important relationship. And that is that if we have a parent distribution with a parent distribution variance here, right, and we take samples from that parent distribution, say of size n, say samples of 3, and you take their mean of each sample, and then you stack up those means. Those means will make a distribution that has a variance that is directly related to the variance of the parent distribution by the size of the samples n, right? So you can see that here in the equation. This represents the variance of means, that's what the little x bar is here, is equal to whatever the variance is of the parent distribution divided by n, which is the sample size used to calculate each of the means. All right? So that means, of course, that this distribution is always smaller, like narrower with a smaller variance as compared to the parent distribution variance. Part of that's because this is a distribution of points, and down here, these are means, and of course, means are going to be closer to the parent distribution mean than any single point will be on average. So one way of thinking of this is that the variance of means is 1/nth of the parent variance. I kind of like that. Okay, let's talk about how we can use that information in the test we call the analysis of variance. So let's turn to this side. Here we can see that we have a parent distribution modeled here. The analysis of variance typically looks at a collection of, say, different samples, and the null is that those samples are all taken from the same parent distribution. So our samples will be samples that each has a mean value. So here we have x bar representing sample A, x bar of sample B, and so on across here. And I've also drawn up here the sample variances of each of those samples. And so what you can see here is that each sample variance is a pretty good estimate of the parent distribution variance. So each of these should estimate the parent distribution variance. Now, these means down here provide some other information. You might notice that that information is related to this distribution here. So in this case, what we're going to do is assume that when the null is true, the average of the sample variances should be a good estimate of the parent distribution variance, and as well, the means of those samples should also represent a good estimate of the parent distribution variance, but we get there using this equation. So we know that our variance of means should be equal to the variance of the parent distribution divided by n. So all we have to do is take our variance of means multiplied times n, and that will give us an estimate of the parent distribution variance based on those means. Now, as you might imagine, if the means are really far apart, they're going to estimate a really big parent distribution variance. If the means are not very far apart, then the parent distribution variance estimate will be closer to that parent distribution. So we put these in a ratio called the F ratio. That is, on the bottom number is the average variance within, which I'm calling the mean of the variances here. And we have 5 of them that we can use to average together. And on the top, we use the variance of means times n, and that is the estimate of the parent distribution variance calculated, again, from this equation, right? So we have a variance of means, and then we take it and we multiply them times the sample size n to estimate the parent distribution variance. Now, clearly, if the null is true, these should both result in the same estimate of the parent distribution. However, if the means are not taken from the same parent distribution and they're really far apart, then their estimate down here from the variance of means will be a very large number, but their estimate from within samples, this parent distribution variance of the average variance, right, will actually be about the same as it is here. So in this case, the F ratio gets really big, much bigger than 1, if the means are far apart, meaning that they're taken from different parent distributions. And so this is essentially the basis of the analysis of variance. When the F distribution, the F ratio gets big, it's very unlikely to occur when everything's taken from the same parent distribution, so a low p-value. When the F ratio is small or close to 1, that means it's pretty likely that you could get that particular outcome when all the samples are taken from the same parent distribution. So that would result in a fairly high p-value, or greater than 0.05, and probably the p-value down here will be much less than 0.05. That's analysis of variance in a nutshell.